Hi, my name is Melody, and my concentration here at Gallatin is the history and philosophy of intelligence. So today, I'm going to talk to you all a little bit about both human intelligence and artificial intelligence. And the goal is that by the end of my talk, I'll be able to explain to you why this, a Roomba, is actually really intelligent. So I'm going to start off by asking all of you to think of someone or something that you think might be intelligent. Chances are you probably thought about someone like this, Albert Einstein. You might have thought about the world's first computer programmer, Ada Lovelace. There's a chance you might have also thought about the brain. Or if you went down a more futuristic path, there's also a chance you might have thought about some sort of robot. Well, the thing that all of these pictures that I just showed you, and most traditional definitions of intelligence, is the fact that they actually have something to do with the mind. This is a commonly held assumption that most people have today, and it was certainly the case that this was a commonly held assumption that most people had when artificial intelligence as a field was just coming together. So let me give you a little bit more historical context. The field of AI as a scientific research field is actually relatively new. It didn't really come around until the mid-1950s and early 1960s, and the term AI was used for the very first time in 1956 during a conference that was held at Dartmouth College. This is also really interesting because this is the same decade that is immediately following the Second World War. And while people do normally associate the Second World War with advancements in the fields of nuclear weapons research and then later atomic weapons research, the fact is that there were a lot of scientific and technological advancements during this war that were really instrumental in forming artificial intelligence as a field later on. So let me give you a few examples. On our left here, we have Alan Turing, who's really well known for his work with British intelligence. He was instrumental in helping the British decode German ciphers that were set by the Enigma machine. But at the same time, this is also when he starts to come up with this idea of a Turing machine, which is a hypothetical machine, which means that he never actually created one that consists of just two parts. One is an infinitely long strand of paper, and the second part is just a table of rules. And it's this hypothetical machine that he came up with during this time that serves as a basis for all modern-day computers that we have now. On our right, we have John van Neumann, who is a mathematician who was really instrumental in helping with things like the Manhattan Project. But he also published this book called The Computer and the Brain, in which he's beginning to explore this analogy that's starting to show up with comparing those two things together. And unsurprisingly, as computer models developed and improved over time following the war, this analogy that van Neumann starts to explore in his book, between the computer and the brain, becomes more and more dominant and popular, especially with AI researchers. AI researchers during this time were really focused on a goal-based sort of intelligence. So they really began to see the computer and the brain as two different types of logic machines that followed a really similar three-step process when trying to solve problems. For humans, the three steps are perception, reasoning, and action. And then for computers, it's also a really similar three-step process where it's getting input of data, processing that data, and then getting some sort of output. Now, the AI research that was happening during the 50s, 60s, and even 70s was really centered around three different institutions, which were Carnegie Mellon, MIT, and Stanford. And one of these computer programs that came out of the three institutions was this program called Shrewd-Loo. Shrewd-Loo was developed by Terry Winograd at MIT in the late 1960s, early 1970s, and Shrewd-Loo consisted of two different parts. As one of the earliest natural language processing computer programs, it had one, a microworld, which is what you can basically see behind me now, which consists of blocks of different shapes, colors, and sizes. The second part of Shrewd-Loo is a robotic arm that can control to move these blocks around within the microworld. So you could be sitting at a computer at MIT and you could have a conversation with Shrewd-Loo and you could type in, "Shrewd-Loo, can you move that red block and place it on top of the green one?" Shrewd-Loo would respond saying whether or not it could, and if it could, it would use its robot arm to do so. Despite the fact that there was so much initial excitement and interest in programs like Shrewd-Loo, AI researchers began to realize that they would actually run into a few problems with programs like this. And the first of these problems is the fact that Shrewd-Loo failed to generalize beyond its microworld. When it's trying to make a plan in order to move the blocks, it works totally fine. But if you wanted to add a few more blocks, or if you want to add objects within its microworld that are more than just blocks, researchers realized that even with the most minor of adjustments, the complexities of the codes that they needed to write actually increased exponentially. And at some point, they realized that they would hit a wall. It's just too hard to make the code more and more complicated. The second issue is that programs like these fail to be flexible. And when I say flexible, I really mean that they fail to adapt to changes in their environment. So in the example we were using before, where Shulu had to move that red block and place it on top of the green block, if for some reason you were to go into the program and just manipulate it so that the red block was misplaced slightly from its original location, Shulu would still try to reach for that block in the same place that it thought it was. And when it didn't find it there, it would just crash. It would have no idea what to do. It couldn't adapt to real-time changes in its environment. So what can we learn from programs like Shulu and other AI programs during this time? Well, I think it actually just shows us that intelligence has much more to do than just being related to the mind. In reality, intelligence also has an aspect to it that has to do with being flexible. You need to be able to adapt to your environment in order to be intelligent. But the really fascinating thing about humans that programs like Shulu don't need to worry about is the fact that we have bodies. We have physical bodies that we need to have control of in order to manipulate things in our environment. But at the same time, while we do have these bodies, we're also constrained by them. So if intelligence also has to do with learning this fit between our bodies and our constantly changing environment, how can we study how this ability is developed over our lifetime? Well, at the Infant Action Lab, a motor development lab right here at New York University, we found that a hammering task, where we ask participants to just pick up a hammer and pound on a peg, lets us do just that. Let me explain to you what I mean. So in the back here, we have the hammering task that we show the adults and the kids. And when adults reach to pick up the hammer to pound on a peg, they usually reach for it using some sort of overhand grip. This is what we call a habitual grip, like you can see in the video behind me, because this is something that you can do almost instinctively. You don't really need to put much thought into doing it. And in this case, this is also the most efficient grip to use, because it allows for the easiest transition into actually using the hammer to pound down the peg. But if we do something as simple as just changing the direction of the hammer that we place in front of you, the most efficient grip to use in that scenario changes as well. So in this case, instead of using that overhand grip that I showed you earlier, the best grip to use is actually an underhand grip instead. And this shows that adults understand that there was a change in their environment and they can adapt their behavior to it. But in the same hammering task that we showed to adults, kids even up to 4 years of age have actually shown great levels of inefficiency when doing it. Some kids will pick up the hammer the same way that the adults do, using the overhand grip and the underhand grip. Some kids will only sometimes change to an underhand grip. And then some kids, like the one you can see in the video behind me, will always use that overhand grip, regardless of what direction that you put the hammer in front of them. So now that we know that 4-year-olds show a great level of variability, now that we know that 4-year-olds show great levels of variability, what are the reasons? What are the sources for this inefficiency and difference between these kids? Well, we used the same hammering task, and our lab just added a bunch of different technologies to it. So our lab is run by Dr. Karen Adolph, and during the task, what we did was we actually added 3 different technologies. We added a head-mounted EEG cap, so we could record their neural activity. We also had them wear these head-mounted eye-tracking glasses, so we could see exactly where they're looking. And finally, we put the kids in a motion tracking sleeve so we can see exactly when and how their hand is moving at all times. And when you put it all together, it actually looks a little something like this. I know it might seem a little intimidating to see the kids do this task, but I can promise you that all the 4-year-olds actually had a lot of fun. We told them that they were robots during the task, so that's actually how we got each of these kids through 60 trials of the hammering, which is really amazing, even for a motor development lab. So what turned out to be different? What did we find was different between the kids who hammered efficiently and those who didn't? Well, surprisingly, we actually found that there were differences in multiple areas. He's smiling, right? He's having fun. With the EEG cap, we found that there were different patterns of neural activity across the trials that were performed by kids who would behave efficiently and those who didn't. With the glasses, we actually found that kids looked at different things too. So the kids who used the efficient grip would look particularly at the hammer or the peg before moving, whereas the kids who were inefficient would look pretty indiscriminately at all parts of their environment. Finally, with that motion tracking sleeve, we found that kids actually moved differently too. So the kids who would pick up the hammer efficiently usually reached for the grip in some sort of like wavy motion for the hammer, whereas the kids who were inefficient at hammering sometimes would go all the way up, then go down, sometimes they'd just start down, and they would do all sorts of crazy motions in between as well. So what can we take away from this study? Well, going back to that working definition of intelligence that we had before, I think that it actually shows us that there's another layer for our definition that we hadn't thought about earlier. And that is that intelligence, or the ability to behave intelligently, or in our case, efficiently, isn't just a result of one simple process or quality that you have. It's not an all or nothing kind of thing. Instead, the ability to do something that we see as trivial as just picking up a hammer and pounding down a peg is actually the result of multiple systems coming together at once and working in a timely fashion for you to be able to succeed on something as simple as that. The 4-year-olds in our task not only had to pay attention to the task, but they had to pay attention to the right things in our task. They had to be able to process all of that information into a working motor plan, and then finally they even had to have the fine motor skills in order to put all of that together and pick up the hammer the way that they intended to in the first place. So now that we have this definition of intelligence here that is far more complex and way more complicated than just having to do with the mind, why did I show you that picture of the Roomba in the first place? What does that have to do with my talk and hammering? Well, that is a great question. Not only can you dress up Roombas, like your favorite Star Wars characters, and have it roam around your house, or post videos on YouTube with your cats riding them around while they're wearing shark costumes, but Roombas actually represent a lot of those qualities that we were talking about a little earlier. For instance, Roombas do sort of come with a kind of mind. And when I say a sort of mind or a kind of mind, I mean that they don't necessarily come with a blueprint of your house. It doesn't know that you have your cat's bed in your bedroom or that your living room's 100 feet wide. But what it does come with is a very simple set of behaviors or responses that it should display when it comes across different stimuli that it can find in your house. For instance, a Roomba knows that if it's roaming around and it comes across a wall, it needs to slow down and turn all 4 of its wheels in a certain angle and at a certain speed so it goes in a different direction and doesn't just crash. It also knows that if its sensors find something in front of it, that it needs to slow down so its vacuums actually have time to do what they're supposed to do, which is vacuum your house. And it's through these really simple interactions with the world and learning how its body should function in its environment that these really small systems within the Roomba that control individual parts of it, like its wheel or its sensor, its vacuum, that can work in tandem and create really complex behaviors that are way more intelligent than just simple vacuum cleaning. So, now that I've walked you through this and we've talked about why a Roomba shows those characteristics of intelligence that we talked about, I also think that it's really important to bring up the fact that those weren't the only factors that we could have been discussing. We could have talked about so many other things when trying to define intelligence, like creativity, pattern recognition, spatial skills, or maybe even empathy. And those are all really important characteristics that we've discovered over time that makes us as humans intelligent and are important for us that we most certainly need to apply when trying to create artificially intelligent agents now, and most importantly, in the future as well. Thank you.